Okay, good afternoon, everyone. I'm Chang from South Korea. Today, I will present on exploring robot-assisted optical current elastography for surgical palpation. This is content of my presentation, and let's begin with introduction. The palpation of underlying anatomy during open surgery is used to detect nerve bundles, arteries, and tumors. The minimally invasive surgical systems do not suffer high fidelity force feedback sufficient for conveying stiffness information to the surgeon. Researchers in past 2 decades have spent significant effort to exploring the utility of tools for digital palpation. Recently, there has been interest in ophthalmology community in exploring the feasibility of using OCT for tissue exploration and local stiffness imaging to enable early detection of tumor onset. Also, feasibility of inducing micro motion control using continuous robot used for 3D OCT imaging was introduced. The contribution of this paper is to offer the first exploration of robot-assisted optical current elastography to leverage information from both of these technologies to achieve a stiffness map. The OCE visualizes the stiffness of sample based on optical current tomography imaging. And the compression OCE is relatively simple and can estimate extensive range of displacement and strain. The pre-experience phase-based OCE require heavy computation phase 11 procedure for calculating large deformation. Therefore, we use a vector method to estimate OCT phase shift between frames to produce the phase-assisted strain map. Also, we use the robot motion to locate the probe and compress the sample. The information of robot motion is used to estimate reference strain to calibrate OCE system. In this work, we propose a robot-assisted phase-sensitive compressed OCE system as a new tool for localized tissue stiffness imaging for the early detection of tumors in soft tissue. Let's move on to system design and method. The relationship between stress and strain in isotropic medium with linear elastic deformation for uniaxial direction can be simplified as equation 1. Here, when uniform stress is applied to the sample using the robot, the strain shows a mechanical property of tissue. And in uniaxial direction compression and displacement, the strain can be expressed as a partial differentiation of displacement. To estimate the strain, we use the OCT system. OCT acquires tomography image based on interference signal. And the OCT signal after press transform is complex number contains phase term. The strain can be acquired from the phase gap between OCT frames. This SDOCT system in OCE use the broadband laser source as a light source and adapt home-built spectrometer for detecting and processing spectral interference signal. And the robotic system is a custom cartesian stage robot with 6 tricks of freedom force torque sensor attached to the end effector. And we designed the plastic probe mounted to the active sensor for tissue indentation and which has a channel for OCT scan beam. The vector methods use the rear and imager term of OCT signals. Pixel intensity and phase are considered as the length and angle of vector on complex plane respectively. And the phase change can be calculated as an angle change of vector summation. The vector analysis method is shown in figure 5. The silicon and other phantoms are used for experiment. OCE strain is different from the robot strain due to the signal-to-noise ratio limit of OCT system and errors in vector-based displacement estimation method. Also, the phantoms are not perfectly homogeneous, isotropic, or linearly elastic. The OCE strain should be calculated to the robot strain. The calibration procedure is depicted in figure 6. We acquired OCE data at 14 different depths and use mean displacement between each step. Now let's see the experimental result. This table shows the experimental result of each phantoms and calculate the Young's modulus are well within the variation reported in the literature for these materials. We fabricate second AGA model and repeat the data collection using robot to evaluate the errors across the different samples without recalibration. The figure A-C shows the results from a second AGA model, and the results show the maximum error at full scale in 19.7%. I will close my presentation with discussion and conclusion. In case of phase-sensitive compressed OCE, estimating strain change along depth direction in tomographic imaging is possible. Our research suggests that the OCE